Welcome to the office. Today we want to take a look at trigonometric substitution. And when we're talking about trigonometric substitution, we're talking about three scenarios. The integrand involves the square root of three different things. We could have u squared minus a squared minus u squared, or a squared plus u squared. So those are the three scenarios that we want to look at. That might seem familiar to some formulas that we already have, but we're trying to generalize those already known formulas just a little bit. So if we take a quick look at trigonometric substitution, again, we're looking at three situations. The integrand involves something like this: square root of a squared minus u squared, or square root of a squared plus u squared, or square root of u squared minus a squared. So these three situations are handled by trigonometric identities. The first one being that if we have a number minus sine, or 1 minus sine squared theta, this is equal to cosine squared theta. So this is a Pythagorean identity, and we can use this. If we multiply both sides by a squared, then we would get a squared minus a squared sine squared theta is equal to a squared cosine squared theta, which is fantastic. Then, so if we see that we have a squared minus a squared sine squared theta is equal to this thing that is a perfect square, then if we were to let u, this thing, be equal to a squared sine, sorry, not a squared, but simply a times the sine of theta, then we have a simplification of this that won't involve a radical anymore. It'll involve a trigonometric function, but it won't be a radical. So that can be helpful. So we let u be a times sine theta, then the square root of a squared minus u squared would become the square root of a squared minus, right? If we let u be a times sine theta, then when we square this, we get exactly a squared sine squared theta, which is nice because this thing we just showed is equal to a squared times cosine squared theta. But of course, we can take the square root then and find that this is just a times the cosine of theta. So we're able to reduce something that involves a radical to something that no longer involves a radical. So we're going to use this substitution to help us do that. The other situations simply, again, use trigonometric identities. For a squared plus u squared, we use the identity that 1 plus tangent squared theta is equal to secant squared theta. And again, multiplying by a squared gives us a squared plus a squared tangent squared theta is equal to a squared secant squared theta. So similarly, what we'll find is if we let u be equal to a times tangent of theta, then the square root of a squared plus u squared is going to be equal to, right? We plug in, perform our substitutions, and this is going to simplify to just a times secant theta. And we have techniques for evaluating integrals that involve secant and tangent, so that's fantastic. We have methods for evaluating integrals that involve sine and cosine, so that's fantastic. And then in our last situation, if we have u squared minus a squared, we want to make use of, right, essentially this same relationship here, just rewritten. So if we subtract 1 from both sides, we see that secant squared theta minus 1 is equal to tangent squared theta. And again, multiplying by a squared gives us a squared secant squared theta minus a squared. So we have a variable minus number. This is going to be equal to a squared tangent squared theta. And then, of course, finally, if we let u be equal to, all right, we have variable minus a squared, so we want this variable minus a squared, or variable squared rather. So let u be a times secant theta. Then when we make that substitution, we will see that u squared minus a squared, right? Make the substitution, plug it in, perform our simplifications, and we'll find that this is simply a times the tangent of theta, which is fantastic, right? Evaluating integrals that involve sine and cosine, evaluating integrals that involve secant, evaluating integrals that involve tangent. We can do those with the methods that we have learned at this point. So we can make these substitutions to help us evaluate integrals involving radicals of this form. All right, so we want to take a look at some examples of this. So we'll do that in our next videos. So I'll see you back in the office here shortly.